Man, those kids looked like they were having a lot of fun.
And learning a lot, too.
Well, just like NASA Connect teamed up with a school to learn about electromagnetism, NASA's teamed up with a university to help us understand propulsion in space.
Hey, let's head to the University of Michigan and see what they've been working on.
I'm Professor Brian Gilchrist with the University of Michigan in Ann Arbor.
And I'm Jane O'Weiler, a graduate student in Space Systems Engineering here at the university.
My students were asked to design, build, and test a very small spacecraft that will be used with NASA's PROCEDS tether mission. PROCEDS is demonstrating a new kind of propulsion technology that does not require any rocket engines. It uses the Earth's magnetic field to help push and pull on spacecraft. PROCEDS will pull down a large, used-up rocket stage.
We named the satellite Icarus after the character from Greek mythology. As you might know, Icarus and his father Daedalus were trying to escape from Crete using wings that they'd built. Icarus flew too close to the sun, and the wax that was holding his wings on melted, and he fell into the Aegean Sea. The PROCEDS mission will be successful if it can rapidly bring down the rocket engine from orbit, which will ultimately burn up in the atmosphere, falling from the sky, just like Icarus. The Icarus satellite will pull out 15 kilometers of tether from the deployer, and the instruments on board will measure the location of the end of the tether, the end mass, and spacecraft attitude.
Did she say attitude?
Not that kind of attitude. I mean the position of the spacecraft relative to the Earth.
Right, Jane. The students designed this satellite to collect this information and transmit the data to the ground. Mission scientists will use this information to better understand the dynamics of tether systems.
To build our satellite, we used computer design tools and a lot of discussions and mentoring from experienced engineers and faculty at Michigan, the NASA Marshall Space Flight Center, and from industry partners such as TRW. After the design work, various mechanical and electrical components were purchased or built. These pieces were carefully put together, and then we were able to begin a long list of tests to see if it was going to work the way we wanted it to.
At the same time we were designing the hardware, we were developing the computer software. Not everything worked the first time, as is typical of anything new being developed. So we had to consider what could have gone wrong, read through the notes and journals to check that we did everything right, and then try again. And sure enough, some changes had to be made to get it ready for delivery in flight. Each step required careful planning to accomplish the special steps that we mentioned earlier. The tests were done here in our labs at Michigan and at the Marshall Space Flight Center.
How did you gather the data?
Electronic sensors were often used in our tests to make the critical measurements necessary to know that the Icarus satellite was still working correctly. But other data collection involved just looking at the satellite to see that, for example, our solar cells were not broken, and sometimes we had to measure how much power the solar panels could generate, or how much power our radio transmitter was sending to its antenna.
Wait a minute. They're in Michigan,
And we're at the Marshall Space Flight Center in Huntsville, Alabama. How do they do that?
Good communications in a project like this is very important. When the students were designing and building their spacecraft, they communicated with their NASA partners using presentations, written reports, and through email using the internet. Later, as we were collecting data, we dealt with the test reports that showed how the satellite and its instruments performed. By using patterns, functions, and algebra, they were able to prove to themselves and NASA that the Icarus satellite was ready for flight. Being able to understand data in the form of charts and graphs is a lot easier than descriptions. Mathematics is really like another language, a language that all of our partners need to understand to be able to work together.